Dr. Scoggin has tripped and spilled the backpack full of sodium chloride crystals he normally carries into his heated alligator pond where his beloved pet Terrabite lives. And Dr. Scoggin would do anything for Terrabite, so he immediately calls his usual deionized water delivery service to come and help him restore Terrabite's preferred salt concentration of 1.9% to the 13 cubic meter aquatic habitat where Terrabite lives. When the DI guy arrives, he uses a conductivity sensor and figures out that the salt concentration has increased to 1.94% salt due to the salt crystals that Dr. Scoggin spilled. So the DI guy pumps the correct amount of DI into the pond to bring the concentration back to the preferred salt concentration. Well, while this is happening, Dr. Scoggin suddenly realizes that the water that is being pumped into the pond is quite chilly. So he measures it. It's 12 degrees C, and it's making his beloved alligator cold. And so he decides that he had better turn on a heater that he has that's sitting in the water so that he can heat the water back up to the preferred temperature. The heater has a power rating of 2150 watts, and the water that that the alligator likes to live in, the alligator prefers it to be 33 degrees C. Now we're going to assume here that zero heat gets lost to the surroundings, which may or may not be a good assumption, but for the sake of this problem, we'll kind of solve it under that assumption. And we're going to figure out how much time he's going to have to leave this heater on to bring that temperature back up to the temperature that is preferred by his beloved pet Terrabite. The other little assumption that we're going to make along the way is right here. We're going to assume that regardless of salt concentration, right here, this is where we see this assumption, regardless of salt concentration, we're going to assume that the water maintains the density and heat capacity of DI water. All right, so this is basically a problem that has two stages. The first stage is where we do a material balance problem in order to figure out just how much water the DI guy probably added. And then we need to do a second part of the problem where we figure out how much time it's going to take for that heater to more or less heat up that charge of water that was added by the DI guy. So let's start here with a little material balance diagram. I'll just do that right here, where we have one type of information coming in here. This is basically the amount of water that's already in the pond before it gets started. And you might notice here that it was given as a 13 cubic meter aquatic habitat. What I'm going to do is convert that volume into a mass so that we can compare it against maybe the masses of other flows that come in and out. So to do that, basically what we'll do is we'll take 13 cubic meters and we'll multiply it by the density of water, which is going to be 1,000 kilograms per cubic meter. All right, and this just is 13,000 kilograms. And that's what comes in on this flow right here, 13,000 kilograms. All right, what else do we know about that flow? Well, we're going to assume that the water is really just made up of pure water, DI water, and salt. And so we can specify down below here how much salt was originally in the water based on the measurement that was taken by the DI guy. So this is 1.94% salt. We're going to express that as 0.0194 down below. And that basically means that we are 98.06% water. All right, the material balance problem that we're figuring out is basically one where pure water is being added in order to bring the concentration back to what our desired concentration is. And we don't know how much that is going to be added, so we'll just declare that as a variable, just say that's x. But we do know that that is going to be 100% water, so I'll just state that right here. And once that water is added, it allows us to get to kind of a different amount of water here. And that amount of water should now be at the salt concentration that we desired, which is going to be 0.19. Right, 0.019 is 1.9%. All right, and that means that what's left over there is just 0.981, or 98.1%. So based on this, we should be able to write mass balance equations. All right, so we'll start with an overall equation. So the overall equation says that we have 13,000 kilograms. So this is our overall. $13,000 kilograms of water plus the amount of water that was added by the DI guy. The mass of that water is going to be equal to the total amount of mass that we end up with on the other side. Okay, so that's the overall balance. We can then use a balance of one or the other of the components that's in there, and I'm going to suggest that we look at the salt balance. There's a specific reason why I want to do that. The reason why is, if you might notice here that flow X, basically where the DI guy adds water, there's no salt that is added there. And so that makes this equation simpler because it eliminates X as a variable. So what we have here is 13,000 kilograms multiplied by the composition that is salt, right? So we multiply it by 0.0194. This now is going to be equal to Y, which is the mass of water that we have at the end, multiplied by the percentage of that water that is salt. So we multiply by 0.019, expressed as a decimal. Well, this is nice because this expression right here is easily solvable for Y. Okay, and so we can do that, basically by just doing 13,000 times 0.0194 divided by 0.019. And that would be the solution to this expression to find Y. So 13,273 0.68, and that's going to be in kilograms. Okay, well, once I know that, I can plug that information into the first equation that I wrote. Plug that in right there, and it will allow me to solve for X. Okay, so if I rearrange this a little bit, we can say here that X is going to be equal to Y, which is 13,273.68 kilograms minus 13,000 kilograms. And when I figure that out, I just basically subtract 13,000 from what I had originally, and it tells me that this value has to be 273.68. kilograms. All right, but we'll notice here that that is not the final result that we want, because what it's asking for is how much time do we have to plug in this heater in order to bring the temperature back up to what the preferred temperature would be for the pond. So I'm going to use a little bit of logic here and say the rest of the water was already at the desired temperature. So the heater's job is not to heat up all of that water. The heater's job is to just heat up the water that we had to add, which is what we just found. We found that 273.68 kilograms of water had to be added. And so what we're going to do is a quick computation to figure out for that mass of water how much time would this power of heater need to work. Okay, so what that equation looks like is this. We can take that charge of water, 273, so this is our energy balance if we want to put a heading on it. Okay, this charge of water, which is important because our basic equation is mass times specific heat times the change in temperature, is the change in internal energy. Okay, and that change in internal energy can be found based on the power of the heater and the amount of time that it's on. So that's kind of our basic equation that we're going to be using. And so we have that mass now of 273.68 kilograms multiplied by C sub P for water. Most of you have probably had to use this enough times to where you know that our typical value we use for the C sub P value of water is 4180 joules per kilogram degrees C. And then we can specify a change in temperature. So keep in mind that the original temperature for this water was 12 degrees C, right? And it's being heated up to 33 degrees C. And so when we come up with what the change of temperature is, we take final minus initial, right? That water that we're adding was initially at 12 degrees and it goes up to 33 degrees. So it would be 33 degrees C minus 12 degrees C. And this is going to be equal to the amount of energy that was added due to the heater. That has to be added due to the heater. So the basic equation there is basically electrical power times time, and electrical power is given to us directly. So I'll just say this is P times T. Right, and that gives us energy, and the reason for that is that power is a rate of flow of energy. So we know here that the power of the heater is 2150 watts. All right, so I'm going to plug that in right here. And that is going to be multiplied by a period of time. And if we don't change anything here, what we'll notice is that we have joules on the left side, and if we have watts on the right side, you might keep in mind that a watt, all right, a watt is a joule per second. So the time basis that we're probably going to find when we do this calculation is going to be seconds, so we'll just keep that in mind. All right, so let's plug these values in. So I have this 273.684. All right, times 4180 times the difference between 33 and 12. And I'm going to use a technique here where I use an equal sign. I get that by hitting alpha, and then above this calc key you see there's an equal sign right there. I'm going to set this equal to 2150 times x. And it's not that this equation would be hard to rearrange manually or anything like that, but since the calculator will solve these types of equations, it's just as easy that I enter it like this. Once I've entered it, I can hit Shift Solve, Shift key, and then above the calc you see it says Solve. And the number it shows right there is an initial guess that's going to be used. I won't get deep into that, but it's just something that is needed for the numerical technique that is being used internally in the calculator. All you have to do once you've done that is then hit equals, and it will solve for t in this case. So t ends up being 11,173.9. I don't really care about that. Let's say 11,174. Okay, so I'm going to plug that right here. I'm going to write it right here. 11,174. That's in seconds, right? We talked about that just a second ago, or just a moment ago. We're saying here that t is 11,174 seconds. Okay, well, that's not hours, so we basically need to do another conversion here in order to get this to hours. And that conversion, if you're not familiar with it, it's 60 seconds in a minute and 60 minutes in an hour. And so that comes up, what we come up with there is 3,600 seconds in 1 hour. So we multiply by that conversion, and it allows us to find a t value. So we take that. By the way, that number that is stored in the calculator is already in variable x. So if I call x and then divide it by 3,600, that gives me a number of hours. And so it ends up being 3.10 or so. Okay, and that would be answer D. So I hope this has been a helpful example, and if it has, I'd appreciate if you'd hit the thumbs up and also subscribe to the channel. And I hope you have fun studying for your exams.